This figure right here illustrates the concept of effective stress. So if you apply a total stress sigma, which we can also express as or write as S, if you apply that stress on a porous medium that is saturated with fluid like this, what happens is, you recall stress is force per unit area, right? So this is the total area that the stress acts on, AT. Well, we can partition that area into two. The ones in yellow, right here, very small, right? Which is precisely the area of the interface between two grains. And the remaining area, which is the one, or which are the ones in blue, are the area corresponding they are the areas corresponding to the fluid, right? So AT is basically A, area of the solid grains, plus area of the fluid. Now, the stress that acts through this area across the solid grains is the effective stress. And the stress that acts across the blue, across the area of the fluid, that is pore pressure. So that's how we partition effective stress, total stress, into effective stress and pore pressure. And this is a fundamental expression, but in the simple form, we neglect this. And that is the simple effective stress we have talked about, which is also known as the Terzaghi effective stress. It's just saying that total stress equals effective stress plus pore pressure. Why do we have this identity matrix? Because this is a tensor. These are tensors. Pressure by itself is a scalar, so we multiply it by the identity matrix like I had explained before. 1, 1, 1. Everything else is 0, so that you have pressure along the at the diagonals. Now recall that in petroleum engineering, compressive stresses and compressive strains are positive, whereas in engineering, tensional stresses, tensional strains are considered positive. So that will change this definition here. So effective stress is the component of the stress taken by the soil skeleton. So the skeleton bears some of the stress. That portion is the effective stress. The remaining portion of the total stress is the pore pressure, which is borne by the fluid. Pore pressure acts in such a way that it compresses the solid grains. So pore pressure is considered to be compressive and is positive if you're using the petroleum engineering convention. Why do we say pore pressure is compressive? Pore pressure is the pressure in the fluid, right? And the fluid is sitting in the pore spaces. When you increase the pressure of the fluid in the pore spaces, it wants to expand, right? But it doesn't have much room to expand because the grains or the solid skeleton are bounding the pore spaces. So it pushes against the grains and tends to compress the grains. That's why pore pressure is considered as positive when you assume compressive stresses are positive. What happens to this equation if you're using the engineering convention and not the petroleum engineering convention, where compressive stresses are now negative? Well, this sign changes and it becomes positive. And we'll talk about that in the next couple slides. Knorr and Bailey generalized the simple effective stress to apply to consolidated or cemented rocks and other materials. So the simple Terzaghi effective stress principle basically applies to unconsolidated or weak sands. But when the sands have been consolidated, then we need an improved effective stress. And that improved effective stress or modified effective stress is actually exact for the problem of volumetric strain. And there is proofs on this which we are not going to get into. But the moral of the story is this is the new, that is the exact effective stress. And what's the modification? We only introduced one constant, which is called the Biot coefficient. So previously there was no alpha, right? Now without the alpha, the equation is the Terzaghi effective stress. With the alpha is the exact effective stress or Biot's effective stress. And this is the definition for Biot's effective stress. What is K? Bulk modulus of the drained rock. So it's the bulk modulus of the skeleton. And the skeleton is a porous medium without the fluid. What's Ks? Bulk modulus of just the sand grain. So as you can probably expect, the bulk modulus of just the sand grain will be greater than that of the grain and the pore structure, because there is some empty spaces, right? So the grain by itself will be a lot stiffer than the grain and the pore. So bulk modulus is an indication of the stiffness of the material. So if K is much smaller than Ks, then this ratio tends to what? 0, right? Because K is much smaller than Ks. Ks is much greater than K. So that tends to 0 and alpha tends to 1. And that's what happens in weak and unconsolidated sands. And when alpha tends to 1, then it simplifies to the Terzaghi effective stress. But for most rocks, it's actually a lot greater than, a lot less than 1. This is common, about 0.5 to 0.66. In most rocks, Biot coefficient is about that value. But as the rock gets more compacted, like shales, which are very compacted and they have low porosities, then Biot coefficient actually is much smaller. Biot coefficient for shales is about 0.2. And it controls the degree of the coupling between the mechanics problem and the flow problem. Remember, we had used the Maxwell's conceptual model, which was a Hooke's law spring corresponding to the mechanical problem and a damper or dashpot, which corresponds to the fluid problem. So the coupling between those two is controlled by alpha. And we'll talk more about that when we look at the governing equation for flow. So we modify the equation for flow in porous media to account for that coupling. And there is one term that shows up in the storage term. All of this will make more sense when we get there. But we have this term. The change in the volumetric strain with respect to time. The volumetric strain is coming from the mechanical problem, right? And now, when we want to apply that to the flow equation, there are other terms in the flow equation, we scale it by the Biot coefficient. So that's how it controls the degree of coupling between the flow problem and the mechanical problem. Question for you: what will the alpha value be? What will the Biot coefficient be for a material that has absolutely no porosity whatsoever? Well, again, you look at this equation. When the material has no porosity, then K equals Ks, right? The skeleton equals the grain because there is no pore network structure. So this ratio becomes 1, and 1 minus 1 is 0. So alpha equals 0 when porosity equals 0. And that kind of material will be like metal that has no pore structure. And there's no concept of effective stress because you just have total stress. So you'll be applying Hooke's law directly on the total stress. There will be no pore fluids. That material will not get the stress will not get partitioned into the pore fluids and the matrix. All you have is matrix. So there will be no pore pressure influence. What about the other extreme, which we talked about, where alpha is close to 1? We have an extremely compliant porous solid, and we had said those are weak and unconsolidated sands, and those have the maximum pore pressure influence. So this value is 1, and you have a stronger coupling between the mechanical problem and the flow problem.